In this video, we're going to look at the connection between electrochemistry and thermodynamics. And we'll do that in the context of a case study looking at a specific electrochemical cell. So first, let's look at our case study reaction and analyze its thermodynamics. So once we have our electrochemical cell notation, we should take that and translate that into an actual chemical equation. And of course, we have to make sure it's balanced. All right, so we can say on the left-hand side we have our anode. So our zinc is going to be oxidized. So we've got zinc solid. It's going to be oxidized to form zinc ions. So we've got our cathode where we've got silver chloride being reduced from silver +1 down to silver metal, silver 0. Okay, so we've got silver chloride, and that's being reduced to just metallic silver. And we can tell this isn't going to be balanced. This is a 1 electron reduction. This is a 2 electron oxidation, so we're going to need 2 of these for every 1 of the zincs. All right, so now we have a balanced equation. We can check it's balanced by looking at the material balance. We can also look at the charge, and this doesn't look quite like it's balanced because this is +2, there's no charges over here, but we've forgotten the chlorides. Of course, this is going to generate 2 aqueous chloride ions. Okay, so we can see it's balanced. Great. Now let's look at the thermodynamics. So we have to look at the thermodynamics for everything present in the reaction. So let's make a little table that has the heats of formation and third law entropies for all the species in this reaction. Okay, so we've looked up the heats of formation for all the different species in the reaction and also the third law entropies, the absolute entropies for all the different parts of the reaction. And you can look this up in an online resource or perhaps in the appendix of your textbook. Great. So once we have these numbers, we can do products minus reactants, taking into account all the coefficients in the reaction. We can't forget that we've got to multiply all the data for chloride by 2, silver chloride by 2, and also all the data for silver by 2. So we do products minus reactants, and we can get the delta H and the delta S for the reaction. So I'll put that on the next page. Okay, so we've calculated the heat of the reaction, we've calculated the entropy change for the reaction, and that allows us to get the standard Gibbs energy change for the reaction. So delta G is delta H minus T delta S. And those are all standards, so we plug in our numbers. So let's assume we're doing this at 298. All the data we looked up were taken at 298 as well. So we've got negative 234,000, because these were kilojoules, joules per mole, minus 298 kelvins times our delta S, which was a negative 148 joules per mole per Kelvin. So we can see we're going to be canceling our kelvins, and so we end up with joules per mole subtracted from joules per mole, so our units work out, and we end up with delta G standard being negative 189.9 kilojoules per mole. So we convert that back to kilojoules. Okay, so we've got delta G standard. So we've got delta G standard, but how does that relate to the voltage of the cell? So what's the connection between the standard cell potential and the standard delta G? Well, one is going to be in terms of volts, and the other is in terms of energy. Well, first let's start by remembering that delta G standard is going to be related to the work, the electrical work that can be done on a system. So what's the work going to be equal to? Well, work is going to equal to charge. So it's equal to charge times voltage. And charge is going to be expressed in coulombs, which is symbol C, and voltage with the symbol volts. Okay? And a volt is defined as a joule per coulomb. So we can see that if we multiply coulombs times volts, we're going to end up with units of joules, energy units. So what charge are we transferring? How much charge are we transferring when we run a chemical reaction? That's going to be equal to the moles of electrons times the charge on 1 mole of electrons. And we can write this out symbolically, and we'll call the mole of electrons. We'll use the symbol N since we tend to use that for moles. And then the charge on 1 mole of electrons we could take, if we wanted to, we can say, well, we've got 1 mole of electrons, and we'll multiply it by the electron charge. And if we did that, we remember that this 6.02 times 10 to the 23rd, and this, you may remember, is 1.6 times 10 to the negative 19 coulombs. But what we do is actually combine these into one giant constant. So what we're going to do is call this whole thing F. It stands for Faraday's constant. We multiply this together. Remember, Avogadro's number has units of 1 over mole. So this is going to give us coulombs per mole. So the Faraday constant, coulombs per mole, is 96,485 coulombs per mole. But you can see it's not really a new constant. It's just the charge on an electron times the number of things in a mole. So if you have a mole of electrons, this is what your charge is. So you could just make up Faraday's constant by multiplying these two numbers together, and you'll get this. This actually has a few more sig figs because I rounded a little bit here. So notice that once we define Faraday's constant, we can say that the charge on a mole of electrons, or the charge transferred in a reaction, is the number of moles of electrons transferred in a given reaction times Faraday's constant. So we know in some reactions we might be transferring, for every step the reaction takes forward, 2 moles, or maybe 1 mole. So for instance, in our example reaction, if we go back and look at it, we can see that we're transferring 2 moles of electrons because we're going from zinc 0 to zinc plus 2. So that's a 2 electron transfer. It just is equivalent to look at the other half cell and say we've got this going from plus 1 to 0, so it's 1 electron, but there's 2 moles of that. So that means that this is a 2 electron reduction. So a 2 electron reduction, a 2 electron oxidation, whatever you look at it, it is still a 2 electron process. So the N for our reaction is going to end up being 2. That allows us to go back and forth between the voltage world and the energy world. So the final equation we're going to write is going to get us back and forth between them. We can see delta G standard must be equal to N and F and the voltage, which we call E standard. So voltage times the Faraday's constant times N. Now there's one thing we have to be careful about. The charge on an electron is not 1.6 10 negative 19 coulombs, it's negative 1.6 10 negative 19 coulombs, right? Electrons have a negative charge, and that's where this negative sign comes from. So this is our final equation that allows us to go back and forth between energy thermodynamics and voltage thermodynamics. Okay, so we have to look at our balanced equation to get how much electrons are being transferred, and we have to use Faraday's constant, and don't forget the negative sign. So let's do this for our reaction. So our reaction, we said delta G standard was equal to negative 189.9 kilojoules per mole. So let's find E. So delta G standard is equal to negative NF E standard. So we can solve for E. E standard is negative delta G standard over NF. And for our reaction, we had 189,900 joules per mole. Okay, so we said there were 2 electrons being transferred since we're having a 2 electron process here. And we put in Faraday's constant, 96,485 coulombs per mole. And so now we can cancel our units. We've got per mole canceling. And we're left with joules per coulomb, and that's a unit of a volt. Notice we made one sign error here. This number is a negative 189. Let's put that in there. Then we have the negative from the equations. Those cancel. This is going to give us a positive E standard. So E standard comes out 0.98 volts. That's the voltage we'd measure under standard conditions. So in other words, if all the concentrations of our aqueous species were at 1 molar. So to find the voltage on an actual cell, we'd actually have to know all the concentrations, and that's the subject of the next video.